Welcome to AI Paper Slop, where we strip away the hype and get straight to the architecture, the math, and the mechanics of the latest ML research with you.
Hey, everyone.
So today we were doing a deep dive into the source material, a pretty fascinating paper. It is called an empirical study of training pixel space text-to-image diffusion models.
Yeah, which is quite the mouthful of a title, but the implications are massive.
Right, totally. So here is the bottom line for you right out of the gate. We all basically know that pixel space diffusion is sort of the holy grail, right?
Oh, absolutely.
Because outputting raw RGB avoids the whole reconstruction bottleneck of a VAE, or variational autoencoder, meaning you don't lose that high-frequency fine detail.
Exactly. And, it entirely cuts out the VAE decoding latency during inference, which is a huge bottleneck in production.
But, and this is the big but, training a pixel space model from scratch is just a computational nightmare. It is agonizingly slow compared to latent-space model.
Right. It's just really stubborn to optimize.
So this paper basically provides the definitive post-training recipe to kind of get the best of both worlds. The blueprint is essentially this. You start with a model pre-trained in latent space.
Right. You take those weights.
Yeah, initialize your pixel model with those weights. Then feed it a really specific mix of self-generated synthetic data and real images. Switch your objective function to X prediction. Swap out your heavy decoder for a lightweight convolutional DiP head. And finally, you empirically calibrate your noise scale to account for the jump in spatial resolution.
Yeah, and the results are pretty wild.
Seriously. If you do all this, you get pixel space models that match or even beat their latent counterparts, but they run up to 4.75 times faster. We were talking about like 0.2-second inference on an H800 GPU.
Which is insane for high-fidelity generation.
Totally. So to really understand how they engineered this escape hatch out of latent space, we have to look at the fundamental optimization problem first. Why is training in pixel space from step one such a, stubborn bottleneck?
Well, the authors proved just how severe this bottleneck is by running a massive controlled ablation study. They used the Z-Image framework.
Which is a state-of-the-art text-to-image architecture, right?
Exactly, yeah. And they trained two parallel models on a massive data set. We're talking 20 billion image text pairs.
Oh, wow. 20 billion, that's no joke.
Not at all. And everything in the training configuration was completely locked in and identical. Same compute budget, same hyperparameter tuning philosophy, the exact same model backbone.
So a true apples-to-apples comparison.
Right. The only variable was the operating space. So one model generated latent representations and the other generated raw pixels.
And how did that shake out?
The latent space model just vastly outpaced the pixel space model. It grasped global object structure, geometric layouts, and the text-to-image semantic alignment exponentially faster.
And I imagine the pixel model eventually caught up, or no?
Actually, no. Crucially, as training progressed, the pixel space model never caught up. Given the exact same FLOPs, latent space always won.
So we know we want the final output to be an image, right? Just a standard grid of pixels. Forcing a neural network to learn this intermediate, heavily compressed, mathematically abstract language just to translate it back into an image later feels inefficient.
Yeah, intuitively it does.
So why does the model stumble so hard when we just ask it to look at the actual image from the start?
Well, it really comes down to the optimization landscape. I think we tend to view a VAE in latent diffusion models as, merely a computational compressor, like a utility just to shrink spatial dimensions to save VRAM.
Right, just a zip file for the GPU.
Exactly. But a VAE is actually a learned, highly structured visual representation. It has already done a massive amount of heavy lifting for the model.
Because it maps high-dimensional, noisy, raw pixels into a lower-dimensional space.
Right, and in doing so, it actively suppresses high-frequency noise and local redundancies. So when you train a diffusion model in this latent space, you are essentially handing it a clean, semantically dense signal.
That actually makes me think of an analogy for you listening. Imagine you are trying to teach a brand new art student how to paint a masterpiece.
Okay, I like where this is going.
Training a pixel space model from scratch feels like demanding that student master high-level composition, dramatic lighting, and complex human anatomy.
While simultaneously forcing them to go out into the yard, dig up dirt, crush beetles, and mix their own raw chemical pigments from scratch just to get the color red.
Yes, exactly. The cognitive load is just way too high. The student spends all their time trying to figure out how to basically make paint instead of learning how to paint a face.
That's a perfect way to look at it. The VAE's latent space hands that student a pre-mixed, perfectly organized palette of colors.
Right.
But in pixel space, the diffusion model has to discover all those basic visual regularities, like how adjacent pixels share color, how edges form, and it has to do it directly from a wildly high-dimensional raw signal.
Which is just a massive amount of noise to sift through.
Exactly. It has to figure out those fine-grained local statistics while simultaneously trying to understand complex global structures like, what does a dog look like? And how does that map to the text token for dog?
So the gradient updates just get pulled in way too many directions?
Yeah, and the optimization process just slows to a complete crawl. So the authors realized that direct pixel space supervision is fundamentally suboptimal for the pre-training phase. You just need the latent space to build that foundation.
Which sets up the core challenge of the entire paper. We use latent space as the training wheels. But how do we transition the model to output raw RGB pixels without inducing catastrophic forgetting?
Right, because you don't want to wipe out billions of compute hours worth of structural knowledge.
Exactly. So what's the first step in that transition?
Well, the foundational step is weight initialization. You don't randomly initialize your pixel space model. You seed it with the weights from the fully trained latent space model.
Oh, interesting.
Yeah, because the generative capacity, the understanding of physics, lighting, geometry, and text alignment, that is all deeply embedded in the attention layers of the transformer backbone.
And those weights are actually transferable across domains.
They are remarkably transferable. When they initialize the pixel model this way, it could form coherent layouts almost immediately. But initialization alone isn't a silver bullet.
Because the neural network's weights are suddenly acting on a completely different domain.
Right. It is expecting compressed latents, and suddenly it's getting raw RGB tensors.
So I was looking at the methodology for this specific transition phase, and the data set they used caught me completely off guard.
The data mix is wild, yeah.
Because the logical assumption is that since we want to escape the VAE and output pristine, uncompressed pixels, we should aggressively fine-tune the model on a massive data set of ultra-high-quality, real-world RGB photographs.
Just flood it with the real thing, right?
Right. But they didn't do that.
Well, they tried, and the model converged at an agonizingly slow pace. The problem is distribution shift. The latent space has a very specific statistical signature. It has its own texture, its own frequency distribution, heavily biased by the VAEs prior.
Right, because the VAE leaves a fingerprint.
Exactly. And raw, real-world pixels possess a completely different statistical signature. If you instantly feed the initialized model a diet of pure, raw photographs, the sudden shift in the underlying data distribution just shocks the network.
The gradient spike.
Yeah, atom optimization goes totally haywire trying to correct the massive sudden loss, and the model destabilizes.
So their solution to this distribution shock was to use synthetic data. Specifically, samples generated by the exact same latent space model they borrowed the weights from.
Yep.
From a machine learning perspective, why does feeding a model its own hallucinations stabilize the training? Aren't we just creating an echo chamber here?
It sounds like it, but the authors frame this synthetic dataset as a low distribution shift bridge. Think about what a synthetic image generated by the source model actually is.
It's an image that the model already knows how to make.
Exactly. Even when decoded into pixels, its underlying statistical structure is perfectly aligned with the source model's existing internal priors. It is the exact conditional distribution the network has spent its entire pre-training life learning.
Oh, that makes sense. So when you train the pixel model on these self-generated images, the loss doesn't spike.
Right. The gradients remain stable. This constrained environment allows the model to preserve all of its hard-earned prior knowledge regarding object structure and text alignment.
While it basically focuses its computational energy entirely on adapting to the new physical format of predicting an RGB tensor instead of a latent tensor.
Precisely. And they proved how fragile this bridge is, too. They ran an ablation where they fed the network synthetic data generated by a totally different architecture, the FLUX2-klein 9B model.
And let me guess, the performance degraded.
It did. It proves that alignment is the critical variable. The bridge collapses if the synthetic data doesn't perfectly match the specific statistical distribution the weights expect.
Wow. But relying purely on self-generated data introduces a fatal flaw, right? I mentioned the echo chamber earlier.
Yeah, you did. And you were right about the risk. The synthetic data inevitably inherits and amplifies the errors of the source model.
Because VAEs notoriously struggle with high-frequency details.
Especially text typography. The latent compression often just mangles small letters. So if you only train your new pixel model on these synthetic images, it will just learn to perfectly output garbled text.
So we need the synthetic data for stability, but we need real data for fidelity. How did they balance the curriculum to get the final model?
They engineered a hybrid data composition. The dataset mixes the self-generated synthetic samples with a subset of high-quality, high-resolution, real images.
So you get the best of both.
Right. The synthetic data maintains the low distribution shift bridge, ensuring the model's geometric and semantic capabilities stay intact during the transition. And then the real images inject the critical high-frequency pixel supervision that was previously lost to latent compression.
So the network actually learns to correct the VAE artifacts. Suddenly the typography sharpens up, the fine textures in skin and hair resolve.
Exactly. It's a really elegant solution.
Okay, so we've ported the weights, and we have this highly engineered data mix acting as our transition bridge. But we are still dealing with a massive change in the physical architecture. The model is now operating in a much larger spatial dimension, and it has to mathematically predict pixels.
Right. The math changes.
Let's look at the objective function, because the authors found they had to fundamentally change the flow matching math from V prediction to X prediction. Can you unpack that?
Sure. So in modern flow matching and diffusion frameworks, the network has different prediction targets it can optimize for. The latent-space model used for the initialization was trained using V prediction.
Which is what exactly?
In simple terms, V prediction asks the model to predict the velocity of the vector pointing from the pure noise state toward the clean data state. And it is highly effective in latent space.
But if we are initializing our pixel model with weights optimized for V prediction, changing the loss target to X prediction, where the model tries to directly predict the clean image itself, seems like a recipe for destabilization.
It does seem risky. You are changing the fundamental question the network is trying to answer.
Right.
But the authors actually found that because the latent initialization is so robust, you can force the pixel model to continue using V prediction, and it won't mathematically explode. It will converge.
Okay, so why switch to X prediction then?
Because when they ran the benchmarks, X prediction consistently yielded superior results on visual quality metrics like Genival and the dimensionality reduction metric, DPG.
Why is that?
Well, in pixel space, predicting the velocity of noise is incredibly chaotic because the space is highly redundant and high-dimensional. Errors in velocity prediction just compound rapidly over the sampling step.
So X prediction forces the model to immediately guess the terminal state, the clean image itself.
Exactly. It anchors the math. It gives the optimization process a concrete, highly supervised target in pixel space, which really stabilizes the generation of fine details.
It makes total sense. But predicting that clean image state is only half the battle. If this model is spitting out raw, uncompressed pixels instead of compressed latents, the decoder head has to do an immense amount of work.
Oh yeah, the physical architecture that maps the transformer's hidden states into an RGB grid.
Right, and the authors tested several decoder heads, essentially running this massive shootout between quality and compute efficiency. Let's look at the heavy hitter first, the transformer-based PT head.
So the PT decoder is an absolute beast. From a pure visual fidelity standpoint, it scored incredibly high.
But I'm guessing there's a catch.
A massive one. The hardware cost is astronomical. The PT decoder alone contains 2.25 billion parameters.
Wait, just for the decoder head?
Just for the head. In the context of a 6 billion parameter backbone, you are dedicating nearly 40% of your total parameter count just to the decoder.
And the FLOPs are completely out of control, right?
Yeah, over 19,700 GFLOPs. For a system designed to improve inference speed, slapping a 19,000 GFLOP bottleneck at the very end of the network defeats the entire purpose of escaping the VAE. You would melt an edge device trying to run it.
Wow. So they looked at the complete opposite end of the spectrum, the GT head. This is a lightweight linear decoder. From an engineering perspective, it's a dream because it's computationally dirt cheap.
Right.
But the visual outputs were flawed. It generated severe grid-like artifacts right at the boundaries of the image patches.
Yeah, and that's because a linear projection processes every single spatial patch in total isolation.
It just takes the token, flattens it, multiplies it by a weight matrix, and outputs the pixels.
Exactly. It has zero awareness of the pixels being generated 1 millimeter over in the adjacent patch. Because the patches aren't communicating during decoding, the edges just don't smoothly align.
So you get this visible checkerboard effect across the entire image.
Exactly.
So you have the PP head, which requires a supercomputer, and the GT head, which ruins the image.
Yeah.
What was the architectural sweet spot?
They developed the DP head. It is a lightweight convolutional U-net architecture. It requires only 834 GFLOPs.
Okay, that is a staggering reduction from the 19,700 GFLOPs of the PT head.
Huge. It is highly efficient, but it completely eliminates the grid artifacts seen in the linear GT head.
So what is happening mathematically inside that U-net that allows it to punch so far above its weight class? Like, why does it fix the grid?
Well, it comes down to inductive bias. Convolutions operate by basically sliding a kernel over the data. They inherently look at local neighborhoods and share weights across spatial dimensions.
Right.
So in the DP head, the features from neighboring spatial patches are forced to interact and blend through these convolutional layers before the final pixel values are even synthesized.
Oh, so it allows the network to communicate across the patch boundaries.
Exactly. Smoothing out the transitions and resolving the checkerboard effect without requiring the massive, fully global self-attention mechanisms of a transformer block.
Brilliant. Okay, so we've locked in the data mix, we shifted to X prediction, and we have this hyper-efficient convolutional U-net decoder.
We're getting there.
But there is a massive physics problem lurking in the flow matching path. Moving from a compressed VAE latent to a raw RGB image means we are dealing with a totally different physical dimension. An RGB image in this setup has an 8 times larger spatial resolution than its latent counterpart.
Right. The scale of the space changes entirely, and because the resolution explodes by a factor at 8, the signal-to-noise ratio, the SNR, in the flow matching trajectory is severely disrupted.
Because the noise schedules in diffusion models are exquisitely tuned.
Exquisitely. If you apply the noise schedule from the latent model directly to the new, larger pixel model, the network is exposed to a variance distribution it fundamentally does not understand. The gradients collapse.
So to recalibrate the physics of the training process, the authors introduce a noise scale factor, which they denote as gamma.
Yes, gamma.
Let's talk about the friction between theoretical math and empirical reality here. Because the theoretical derivation in the paper is pretty straightforward. If the spatial resolution ratio between your raw pixels and your latents is 8, which we call R, and you assume average pooling, the variance of the independent pixel noise should decrease by R squared.
Right.
Following that logic, to balance the SNR, your gamma factor should simply equal R. Gamma should be 8. The math is super clean.
Super clean.
But when they actually trained the models, gamma 8 was heavily suboptimal.
Yeah, and that's because the theoretical derivation relies on a dangerous, simplifying assumption. It assumes that the VAE's encoder functions exactly like a simple linear average pooling layer.
Which it definitely doesn't.
No, a VAE is a deeply complex, highly nonlinear neural network. It does not just linearly average pixel values. It actively reshapes the statistical distribution of the signal, discarding high-frequency information based on learned semantic weights.
So the distribution shift between the latent manifold and the pixel manifold is highly nonlinear.
Exactly. The resolution ratio of 8 gives you a theoretical anchor, but it just fails to account for the nonlinear behavior of the VAE.
So they basically resorted to empirical testing. They swept the gamma values and found that gamma of 2 completely crushed gamma 8 across all visual benchmarks. It stabilized the flow matching path perfectly.
Which is a sobering reminder for ML engineers. Elegant theory only gets you so far. You always have to look at the loss curves.
Seriously. So empiricism dictates the final architecture. With gamma locked at 2, the post-training recipe is complete. But the authors actually took it 2 steps further to aggressively optimize the deployment latency for the end user.
Yeah, they wanted this thing to be fast.
First, they implemented progressive patch size adaptation. Vision transformers chop the image into a sequence of patches. Initially, the patch size is 16 by 16 pixels, but the authors dynamically shifted this to 32 by 32 and even 64 by 64 during training.
And we should really unpack the compute savings there. If you double the patch size from 16 to 32, you aren't just cutting the number of visual tokens in half. You are cutting the sequence length by a factor of 4.
Oh, wow. And since the compute cost of self-attention scales quadratically with sequence length, the VRAM and FLAP requirements basically plummet.
Exactly. And this really highlights a massive structural advantage of operating directly in pixel space. If you try to aggressively compress a latent space model by increasing the VAE's compression ratio, you permanently destroy high-frequency details.
The generation quality falls off a cliff.
Right. But in pixel space, you can dynamically increase the patch size, drastically reducing the token sequence length. And the model still maintains highly competitive visual fidelity because it is still being supervised on the raw RGB target.
Okay, that is super interesting. And they combine that patch scaling with step distillation, right?
Yeah.
Specifically, distribution matching distillation, or DMD. For you listening, distillation is essentially training a smaller, faster student model to mimic the outputs of a slower, heavier teacher model, but in drastically fewer steps.
Right. DMD minimizes the divergence between the distribution of images generated by the fast student and the distribution generated by the slow teacher. It allows you to collapse a 50-step generation process down to just 4 steps.
But wait, latent models use distillation too. Why is it more impactful here in pixel space?
Well, in latent-space models, distillation optimization hits an asymptotic wall. As you distill the denoising steps down to 4 steps, or even 1 step, the denoising process itself becomes incredibly fast.
But you still have to run that latent tensor through the massive VAE decoder to get the final image.
Exactly. That VAE decoding step takes a fixed amount of time. It acts as a hard latency floor. You cannot optimize it away. As the denoising gets faster, the VAE decoder starts taking up 30, 40, even 50% of the total generation latency.
But in pixel space, there is no VAE decoder. When you apply step distillation, you get pure, unadulterated scaling. Every step you remove directly lowers the total system latency. You essentially remove the floor.
Precisely. And when they applied this entire recipe, the latent initialization, the synthetic real data mix, X prediction, the DiP decoder, the empirical gamma calibration, and the step distillation to the Z-Image and FLUX2-klein architectures, the benchmarks were staggering.
I can imagine.
At 100 function evaluations, the pixel models matched or exceeded their established latent counterparts. But with the 4-step distillation, the pixel models delivered end-to-end inference speedups of 3.18 to 4.75 times over the latent baselines.
So we are talking about running a full-fidelity text-to-image generation in roughly 0.2 seconds on an enterprise GPU. That officially crosses the threshold into real-time, ultra-high-fidelity generation.
It's crazy fast.
And the fact that this recipe stabilized both Z-Image and FLUX architectures proves it isn't just a one-off hack. It is a fundamental engineering blueprint for diffusion models going forward.
Yeah, it really forces us to reconsider the standard pipeline of generative AI.
It really does. Looking at the sheer mechanical depth of this transition, it raises a pretty provocative question about the future of these architectures for you to think about. This paper definitively proves that VAE latent spaces are unparalleled for the heavy lifting of initial pre-training. They give the network that clean, structured foundation.
Absolutely.
But for final pixel generation, the VAE acts as a severe computational bottleneck and a liability for high-frequency details. It really makes you wonder, are VAEs merely the temporary scaffolding of generative AI?
That is the big question.
Will future research figure out how to discard the scaffolding from day one without breaking the optimization landscape? Or is this highly engineered, latent-to-pixel 2-step transition the permanent reality of high-fidelity AI? It is a fascinating engineering problem to consider the next time you spin up a real-time generation in your pipeline. Thank you for joining us for this deep dive into the source material on AI Paper Slab, and we'll see you next time.